Hello and welcome to today's webinar. My name is Brenton Harris and I'm the Vice President of Sales and Marketing at Protectowire Fire Systems. I'm a member of NFPA, National Fire Protection Association, SFPE, the Society of Fire Protection Engineers, as well as the FSSA, so the Fire Suppression Systems Association. And what we're going to talk about today in this webinar is how to handle digital linear heat detection, integration, and control equipment challenges with ease. Now, before we get started, there's a few kind of minor housekeeping items we'll go over. There is a live Q&A function that's at the bottom left part of your screen. Some of you might need to scroll, others might be able to see it now. That will be live and functioning during the presentation. Also, everyone who attends now, or at least registered, will be receiving a link later on via email where you'll have a link to go back and review this presentation in case there's any information or data or anything else that you want to verify or use. So with no further delay, let's get started. Today we're going to focus on the integration of digital linear heat detection into a variety of control equipment. There's not going to be a lot of time spent on how to choose your linear heat detector, what environments, operating temperatures, ambient temperatures, jacketing materials, even the technology between our confirmed temperature initiation or our standard digital detectors. And I highlight that because A, we're going to do a couple of things. One, I want to respect your time. And two, though, is that we've actually recorded a series of webinars that go into more detail about how to choose a detector and what the features and benefits are of our different digital linear heat detectors. And those three different webinars are currently available on demand at for the resources page on the Protectowire website, or you can also find them on YouTube. And the three different webinars listed here are the 5 benefits of CTI linear heat detection, which talks about our newest digital linear heat detection technology, a quick guide to installing Protectowire linear heat detection, and as well as an in-depth look at 7 applications for linear heat detection. Now, this slide is going to be a review for many of you out there, but I want to take a moment to discuss the difference between conventional and addressable control panels. At Protectowire, we manufacture and sell conventional control panels only. We do not offer any addressable control panels. With conventional control panels, each IDC, or initiating device circuit, is a single zone. Conventional panels offer hardware-defined zones and often have limited field programming options. They're compatible with all normally open contact devices, so think Protectowire, pull stations, call points, etc., and are often used and/or preferred in industrial applications. An example of an industrial application would be something in power generation. Addressable panels offer multiple zones on the same SLC or signal line circuit. Addressable panels offer software-defined zones and require proprietary field programming. Most addressable devices are only compatible with their own brand as they require a proprietary node. These panels are often preferred in non-industrial applications. An example of that would be an airport or a shopping mall. It's important to note that both of these technologies have their place within the market. Similar to how you'd choose a detection device according to the application, a smoke detector versus heat detector, or a beam detector versus flame detector, knowing the features and benefits of a conventional control panel and an addressable control panel will allow you to choose the correct technology for your application. Next, we're going to focus on Protectowire branded control equipment. First up is our SRP 4x4. This is a small, off-the-shelf, conventional releasing panel. It offers 4 Class A or Class B IDCs, has a single Class B only supervisory, and 4 Class B outputs. It's compatible with 120 or 240 VAC operation. It has a 24 VDC battery charger, ground fault detection, as well as common alarm, trouble, and supervisory relays. It's field programmable via dip switch settings. There are 16 pre-programmed configurations available. Each IDC is capable of supervising up to 10,000 linear feet, or just over 3,000 meters of protector wire. Now, while that's an impressive length, a large number, I caution the audience that we do not typically recommend installing that length of detector on any single zone. If there is a fault condition, troubleshooting almost 2 miles of cable or over 3 kilometers of cable can be a service nightmare. While the SRP 4x4 is a small, off-the-shelf, field programmable control panel, the Fire System 2000 or FS 2000 control panel is the opposite. This light industrial control panel is 100% customizable and scalable. It has the ability to have up to 46 different detection zones. These zones can be configured in either a Class A or a Class B configuration. Each IDC can support up to 5,000 feet of protector wire, or just over 1,500 meters. The panel has 2 general NAC circuits. It offers either 120 or 240 VAC, depending on where your project is based, a 24 VDC battery charger, and a common alarm, trouble, and supervisory relays, as well as hardwired factory programming logic. Some optional features available in the FS 2000 control panel include an alarm point location meter. This helps you to identify the hotspot or overheat location within your zone. We offer auxiliary 1 amp or 10 amp relays for additional alarm or trouble identification per zone, solenoid releasing, water flow detection, and additional NAC circuits. The panel also offers intrinsically safe circuits through the use of intrinsic safety barriers, or ISBs, external key switch operations, and there's several additional enclosures if the standard NEMA 1 or IP20 enclosure is not sufficient. The FS 2000 control panel is really very unique product, can be designed and customized to meet a variety of requirements. Moving on, I'd like to talk about our line of interface modules. Now, in the next few slides, you're going to see some images that are going to look remarkably similar, despite the fact that the 2 modules actually supervise different technologies. So there are some very similar features and benefits that are shared amongst the modules, but the fundamental core technology and operation of the 2, in terms of the linear heat detection side of it, are different. The first module we're going to talk about today is our PIM 530, or Protectowire Interface Module 530. So you can see here it's available without any type of enclosure, or if you have the PIM 530E for enclosure, it comes in an optional NEMA 4X or IP66 rated enclosure. The PIM 530 features include the module's capability to monitor or supervise up to 6,500 feet or 2,000 meters of Protectowire linear heat detection. It's Class A or B field selectable. Because of the LCD screen on the module, it offers integrated alarm point location, meaning that when there is an alarm condition, the module will display the location in either feet or meters. What's more is it has a 64 event history, so first in, first out, date and time, 2 Form C relay contacts, one for alarm, the other for fault, 2 4 to 20 milliamp outputs, 12 to 30 VDC, an optional enclosure that we spoke about on the last slide, and then an ancillary output is Modbus Rtu. It's a serial communication via RS-485. Similar to the PIM 530, we also have the CTM 530 interface module. And this is the module that's compatible with our CTI, or Confirmed Temperature Initiation Series detector. For more information on that technology and how that detector works, as mentioned earlier, I suggest you follow up with one of our other webinars. At first glance, the features of the CTM530 interface module look very similar to the PIM530 interface module, but there are a few important differences. The CTM530 can monitor up to 4,000 feet or 1,200 meters of the CTI linear heat detector and required T-type interposing feed cable. The module is field selectable for either a Class A or Class B configuration. Similar to the PIM, it has integrated alarm point location. It will also, by nature of the technology, because of the short circuit discrimination, it has integrated short fault location. There's individual LED status indicators. There are 4 on this, while there are 3 on the PIM. It's got an LCD display, the same 64 event history, date and time, and note that the CTM530 module has 3 Form C status relays. So we have alarm, fault, and short fault. 2 4 to 20 milliamp outputs, which I'm going to talk more about in a second, a 12 to 30 VDC, the same optional NEMA 4X or IP66 enclosure, as well as the same ancillary output, Modbus output, RTU, via RS485. For our more industrial users, the CTM530 interface module offers 2 4 to 20 milliamp outputs. The first output will give you the status of the module. So a normal condition, an open fault, a short fault, which is mechanical damage, or an alarm condition. The second output is for alarm point location data. That will tell you how many meters or feet into the detection cable zone is either an alarm condition or a short fault condition. While our CTM and CTI technology have the ability to show the temperature on the LCD screen, the temperature is not transmitted via the 4 to 20 milliamp outputs, as you can determine the detector's temperature based on the status output. For normal, everything is okay. For an open, current flow has stopped. For a short fault, it is mechanical damage to the detector below its initiation temperature. And for an alarm condition, the detector has met or exceeded its fixed activation temperature. The CTM530 has 3 Form C relay contacts. They're rated at 1 amp at 24 VDC. There's a common trouble, there is a short fault, and there is alarm relay. In the figure on the bottom left there, connection diagram number 1, it shows how to measure or how to supervise an alarm and general fault condition. Now with this configuration, your IDC from the host panel or your addressable module will only know that there is a fault condition. It will not know whether that fault is an open or whether that fault is short fault from mechanical damage. That information would have to be determined locally by viewing the LCD screen of the CTM530 module. Now the connection diagram number 2 would allow a host panel or addressable module and addressable panel to determine the fault condition remotely. You would be able to determine whether it is a short fault from mechanical damage or whether it is an open fault condition, meaning a break in the linear heat detection cable. A final note related to the relay contacts is that our FM approval and UL listing both require that the relay contacts are supervised by a listed and approved control panel. While we do offer the 4 to 20 milliamp as well as the Modbus, both of those are ancillary outputs that are designed to be supplemental to the relay contacts being supervised. The final CTM530 output I'm going to talk about today is our Modbus Rtu via RS485. As you can see, it's a single port, half duplex, and we offer a variety of baud rates. Typically, with serial communication, you have a maximum distance between devices of about 4,000 feet or just over 1,200 meters. Now, conversely, we've actually seen these monitored using an RS485 serial to fiber optic media converter on a fiber optic network that runs throughout a facility. This allows for significantly longer distances in between each of the CTM 530 interface modules. Let's talk about some features that are only available on Protectowire control equipment. One of those is the ability to have an alarm point location meter in any of our supervision or control equipment. Our PIM 530 and CTM 530 interface modules have integrated alarm point location in their LCD screens. The SRP 4x4 can be ordered with an alarm point location meter, as can the FS2000 control panels. Alarm point location meters are not currently available on other manufacturers' control equipment. However, when there is a short fault condition in the field or an alarm that has been initiated, a standard electrical meter can be used to find the location of the shorted cable. Protectowire PHSC has an approximate resistance of 0.185 ohms per foot or 0.61 ohms per meter. To say it another way, this equates to 5.4 feet per ohm or 1.64 meters per ohm. So you can take an electric meter, like the example here, you read 35 ohms of resistance, you know that your short is 35 ohms times 5.4 feet, approximately 189 feet or 58 meters into the detection zone. Another important point is that all Protectowire linear heat detectors have an incremental distance marker on the jacket. This is done every 24 inches or 2 feet in English measurements or every meter in metric measurements. Further, when the original control equipment is installed, typically copper or Type T feed cable is used to transition from the control equipment to the start of the linear heat detection zone. The resistance value of this interposing feed cable can be eliminated by following the configuration and calibration techniques designed for both our interface modules as well as our control panels. Another consideration when choosing your control equipment is whether you will need a Class A loop or a Class B configuration where your end-of-line resistor terminates remotely in the field. If you look at the illustration on the top right side of your screen, this illustrates a Class A configuration. You have your control equipment, in this case it's a CTM 530 interface module, and typically your feed cable or extension wiring goes out in conduit to a junction box. There it makes a transition via compression terminals, leaves the junction box using a strain relief, and there's your linear heat detection cable out in the field. It returns in a second, or in some cases final junction box, back through a strain relief, where it once again transitions using compression terminals from the linear heat detector to extension grade wiring or feed cable. The return cable is then typically in conduit as it goes all the way back to the control equipment. A significant benefit of a Class A loop is that should there be a break in the cable, you still maintain detection throughout the circuit everywhere except the break. It's important to note that when employing a Class A, wiring polarity is very important and must be followed throughout the circuit. Now looking at the bottom right image, that uses a Class B configuration. The same outbound principles apply as you have feed cable extension wiring, goes out in conduit to a junction box, makes a transition via compression terminals, leaves the junction box using a strain relief, and there's your linear heat detection cable out in the field. When it returns in the second or final junction box back through a strain relief into a compression terminal, that's where your end-of-line resistor is placed on the other side of that compression terminal. The challenge with a Class B installation is that if there's a break or any portion of the linear heat detection cable is shorted, the control equipment cannot supervise the detector beyond the break or shorted point. Another final note is that if the linear detector's metal conductors are the same as in our PHSC, where they're both steel, polarity is not important in a Class B configuration. However, if the conductors are different, like in our CTI technology, polarity is still important and the circuit must be wired correctly. Class A or B configurations are often determined by the job site needs, the application needs, or the control equipment. Many manufacturers other than Protectowire offer IDCs either through their conventional panels or addressable modules that can support both of these wiring configurations. All of Protectowire's digital linear heat detectors can be made intrinsically safe by following FM-approved illustrations and control drawings. All intrinsically safe applications are a Class B configuration only. That means your end-of-line resistor, as we just reviewed, terminates in the field. It does not leave the hazardous location. The FM-approved intrinsically safe solutions offered depend on the type of control equipment you use. We can offer an intrinsically safe system with an entire fire alarm control panel by installing intrinsic safety barriers, either a shunt diode barrier or a DC isolator in our FS2000 control panel. Further, we can offer our PIM or CTM 530 interface modules with an ISB so you can have an intrinsically safe zone on another manufacturer's control equipment. Now, what I've covered here are the Protectowire solutions for intrinsically safe FM-approved solutions. This doesn't preclude our detectors from being used on other manufacturers' control equipment. However, you would need to verify the compatibility and other types of requirements with those manufacturers directly. Moving on, I now want to talk about the electrical and mechanical characteristics of our PHSC and PLR digital linear heat detectors. As you can see here, the primary difference between our PHSC and our PLR detectors is their resistance value per foot or per meter. The PHSC has a resistance value of approximately 0.185 ohms per foot, whereas the PLR resistance is approximately 1/3 at a 0.058 ohms per foot. Their capacitance at 35 picofarads and the inductance at 2.5 microhenries per linear foot are identical. The jacket dielectric with 500 VAC and a conductor voltage rating of 30 VAC or 42 VDC. And all of our detectors here, the EPC, XCR, XLT, PLR, and PLRCR, are a 4 millimeter diameter. In the last slide, we talked about the electrical and mechanical characteristics of these two cables, the PHSC and the PLR, and now we're going to talk about electrically why they are different. So you can see in the top image here, our PHSC detector, which has the higher resistance value, is a spring steel coated in zinc. The resistance value of the steel is inherently higher than that of the lower image, which is a steel conductor with a copper coating and then a further third trimetallic nickel coating on top, which lowers your resistance to 0.58 ohms per foot or 1/3 of the steel. The reason I highlight this is for the balance of this presentation, we're going to discuss other manufacturers and control equipment. Knowing the resistance values of our detectors will allow you to choose the appropriate detector and control equipment for your application. Prior to moving on and speaking about other manufacturers' control equipment, I do want to cover some very basic installation guidelines that are relevant to all control equipment. For our PHSC and PLR detectors, copper feed cable is typically used in between the start of the zone with the control equipment and the first junction box. For our CTI series, it's TX or Type T thermocouple feed cable that's used in between the CTM module and the start of the first junction box. A minimum conductor size of 18 gauge is required. All transitions should be made in recommended Protectowire offered junction boxes, and all linear heat detection box penetrations should use our SR502 or SR502N strain relief, which is perfectly fitted for the diameter of our cable. All terminations inside those junction boxes must be via compression terminals. The PWSC, which is a Euro-style compression terminal, or the DRTB T-2, which is a compression terminal that is a Type T thermocouple for our CTI series. Wire nuts and other non-approved connection methods are considered improper installation and can potentially void warranties. Having spent the first part of the presentation talking about Protectowire branded interface modules and control panels, now I want to talk about some other manufacturers' control equipment. Note that the list we're going to cover here today, that the manufacturers are listed in alphabetical order. First manufacturer we're going to talk about today is Fike, and we're going to cover their monitor modules for the Cheetah XI and CyberCat addressable systems. Let's see the part numbers here on screen. We have a non-isolated as well as an isolated version. Each of those addressable modules will take up one address on the SLC. There's two independent dry contact monitoring circuits, and the key here is the 100 ohms of max wiring resistance. A 39K ohm end-to-line resistor, and these modules are capable of supervising the detector in a Class A loop or in a Class B wiring configuration. Here we have the part numbers for the Cheetah XI and CyberCat addressable mini monitor modules. So you can find the part numbers there. Again, there's a non-isolated as well as an isolated version. Very similar to the standard monitor modules. One address on the SLC, two independent dry contact monitoring circuits, and once again a 100 ohm max IDC wiring resistance, the same 39K ohm end-to-line resistor, and they can support Class A or Class B wiring. On your screen here, you'll find a recap of the Fike products. We've got our standard monitor modules on the top there, and what we've done is we've taken that 100 ohm IDC wiring resistance and actually done out the math in both feet and meters for everybody to understand. So your standard monitor module from Fike can support approximately 500 feet of the PHSC series detector by Protectowire, a 1700 feet of our PLR, that's the Protectowire low resistance, that's that copper-coated detector, and a 4,000 feet or 1,220 meters of our CTI series. And you'll see that that number does not change throughout the presentation because the CTI series requires our CTM 530 interface module to supervise that detector. Now for the mini modules here for Fike, the PHSC series at 500 feet, 152 meters, as well as the PLR series, 1,700 feet and 520 meters, that remains the same despite the mini monitor modules because of the fact that that 100 ohm IDC wiring resistance doesn't change. Now for their SHP Pro conventional releasing panel, you see that that actually has IDC resistance of 440 ohms. That allows you to go a little bit further, and with the PHSC then, you end up with a 2,300 foot zone or 700 meters, and with the PLR, that's 7,500 feet or 2,285 meters. Moving on to JCI and the Simplex AutoCall brands of the 4100 series addressable panels using the IDNet. Once again, we've got our part numbers listed up on screen for reference. The Mini IAM has one address on the IDNet. It's a single dry contact monitoring circuit, 10 ohms of max wiring resistance, and that is designed for a Class B configuration only. Moving on to your dual input addressable module. Again, one address on the IDNet or the SLC, two independent dry contact monitoring circuits, another 10 ohms of max wiring resistance, and note that this module is capable of two Class B wiring inputs or a single Class A loop. Here's a quick summary of the AutoCall and Simplex individual addressable modules distance calculations for Protectowire. So on the PHSC series, you can see that it's 50 feet or 15 meters. The PLR, the Protectowire Low Resistance series, is 160 feet or 50 meters. And the CTI series remains constant at 4,000 feet or 1,220 meters because of its requirement for the CTM 530 interface module. The dual input individual addressable module shares the same 10 ohm max IDC wiring resistance. And so the values for the PHSC remain at 50 feet and 15 meters, and the PLR at 160 feet and 50 meters. The Potter IPA series and AFC series addressable panels also have some addressable modules we can cover here. The PAD 100 SIM single input module is good for one address on the SLC. It monitors dry contacts, has a 100 ohm max wiring resistance, and a 5.1K ohm end-to-line resistor. This module is designed for Class B wiring only. The PAD 100 DIM, or the dual input module, also uses a single address on either the IPA series or the AFC series SLC. However, when two Class B circuits are used in this module, the single address is then divided into subpoints. Once again, the module monitors dry contacts. It has a 100 ohm max IDC wiring resistance, the same 5.1 k ohm end-of-line resistor, and just mentioned a few seconds ago, two Class B wiring configurations, or one Class A loop. Here's a quick summary of the Potter part numbers and the corresponding distances. As you can see, the single input module, whether for the AFC series or the IPA series, has 100 ohm IDC. With the PHSC series, that's 500 feet per zone, or 152 meters. And with the PLR series, it's 1700 feet, or 520 meters. For the dual input module, the PAD 100 DIM, the 100 ohm IDC doesn't change. So we remain at 500 feet for the PHSC series, or 152 meters, the PLR at 1700 feet, or 520 meters, and once again, the CTI series remains constant at 4,000 feet because the requirements for that CTM 530 interface module. The 4410 RC conventional releasing panel has a 700 ohm IDC for linear heat detection only. And how that equates then to the PHSC series is you end up with a 3,500 foot zone, or 1,065 meters, or on the PLR series, it's approximately 12,000 feet, or just over 3,600 meters. The last manufacturer we're going to talk about today is Siemens, the Cerberus Pro, or Decigo control panel monitor modules. So you can see they have a mini IDC module, a single and dual IDC module, as well as a multiple IDC contact output module. There's one address per input on the SLC, two independent dry contact monitoring circuits per input, a 10 ohm max IDC wiring resistance, a 470K end-of-line resistor, and these modules are capable of supporting the detector in either a Class A or Class B IDC wiring configuration. To summarize the Siemens addressable modules, you can see that all of them share a 10 ohm IDC. So whether it's the multi-IDC, the single IDC, the dual IDC, or the mini module, all of them have the same max wiring resistance, which equates to 50 feet for the PHSC series, or 15 meters, and 160 feet, or 50 meters, for our PLR series. Once again, the CTI series maintains 4,000 feet as it requires the CTM 530 module. The last product that we're going to talk about today is the TXR 320 conventional releasing panel. And as you can see from here, the 100 ohm max wiring resistance, 3.9K end-of-line resistor, and it's capable of supporting the detector in either a Class A loop or Class B wiring. Once again, the 100 ohms max IDC wiring results in a 500 foot PHSC zone, or 152 meters, 1,700 feet for the PLR, or 520 meters. In closing, we covered a lot of information today regarding the integration of Protectowire digital linear heat detectors into both Protectowire branded product as well as other manufacturers' equipment. Given Protectowire is defined as a normally open, resistive contact device, the max IDC wiring capabilities of a circuit, combined with the Class A versus Class B wiring configuration, are serious factors in deciding what control equipment to use. Different types of equipment are capable of supervising different Protectowire zone lengths. Some products offer capabilities in IDCs that can support extremely long zones of Protectowire. In those cases, we recommend considering an alarm point location meter or other tools. For example, create a zone map of your system or use an annunciator. These can help you identify where the overheat or hotspot is located. Other products support shorter lengths, which has its own value, as an alarm point location meter is not necessary because you are able to quickly and accurately identify the location of a hotspot in an addressable system. Every piece of control equipment has its place in the market. Today we covered a lot of information related to control equipment. If you're interested in learning more about our linear heat detectors, I urge you to go to protectowire.com, and under our resources page, you'll find additional webinars that exclusively focus on our linear heat detectors and other applications. Finally, I'd like to thank the companies that allowed us to use their products as examples on how to integrate Protectowire into other manufacturers' control equipment today. Should you have any additional questions, please email us, Protectowire, at info@protectowire.com. Thank you for your time today.